Your body was built by a star that no longer has any say in what happens to you once you leave its reach. Past roughly 100 astronomical units, past the last thin edge of the sun's magnetic influence, the particles that arrive aren't sunlight anymore. They're fragments of exploded stars, moving at nearly the speed of light, and there is nothing between them and your cells. Not your skin, not a spacecraft hull, not the shielding we currently know how to build. Most people assume the danger of deep space is the emptiness. But the first thing your body would actually lose a fight with isn't emptiness at all. It's a kind of light you were never designed to survive, arriving from every direction, every hour, for as long as the journey lasts. This isn't speculation. It's documented physiology, measured in the astronauts who've come closest to that edge. Make yourself comfortable. Let's begin. There is a specific, measured place where this story stops being philosophical and starts being physical. It isn't a border on a map, because there's no line to draw out there. It's a moment, recorded by an instrument, on a spacecraft that had been flying since before most of this audience was born. Voyager 1 launched in September of 1977, aimed outward on a trajectory that would eventually carry it past Jupiter and Saturn, and then simply keep going, long after its planetary flybys were finished. For decades it climbed outward through the outer solar system, well past Neptune, into a region so thin and quiet that empty almost undersells it. And then, in the summer of 2012, its instruments started reporting something strange. On July 28th, the detector built to count particles streaming outward from our own sun registered a sudden 50% drop. Days later, the reading reversed, as if the boundary itself were breathing. It did that a few more times, in smaller and smaller oscillations, like waves receding from a shoreline. Then, on August 25th, 2012, the solar particles dropped to nearly nothing and stayed there. In the same instant, a different instrument, built to detect particles arriving from outside the solar system entirely, spiked upward and never came back down. That was the crossing. Voyager 1 had passed through the heliopause, the outer edge of the vast magnetic bubble our sun blows around itself, extending roughly 120 astronomical units, well over 100 times farther from the sun than Earth is. Inside that bubble, everything arriving at a spacecraft, or a body, is filtered through our own star's magnetic field and solar wind. Outside it, none of that protection applies. The particles hitting Voyager's detectors that day hadn't come from the sun at all. They'd been traveling for thousands, sometimes millions of years, born in the deaths of stars in other parts of the galaxy, and Voyager was the first human-built object ever to sit directly in their path with nothing shielding it. It took NASA's team more than a year to confirm what they were seeing, because the data didn't match every prediction cleanly. The magnetic field direction, oddly, didn't shift the way theory said it should, but the particle counts were unambiguous, and by September of 2013, the agency was ready to say it plainly. Voyager 1 was no longer inside the sun's influence. It was, for the first time in the history of any human-made machine, in interstellar space. If any of this sounds like the kind of measured, patiently verified science that makes deep space easier to sit with at the end of a long day, you're already in the right place. This channel exists for exactly that reason, and if it's useful company, staying subscribed helps more of it get made. What makes this moment worth dwelling on isn't the mile marker itself. It's what the mile marker actually represents. Everything about human survival in space, every design choice in every spacecraft ever built, every safety margin NASA has ever calculated, assumes a body operating inside the sun's bubble, inside the heliosphere, inside Earth's own magnetic field layered on top of that, inside decades of engineering built around conditions that exist only in this one relatively sheltered pocket of the galaxy. Voyager crossed a line that no human being has ever crossed, and the instruments on board didn't just mark the moment. They measured, directly and specifically, what changes the instant that protection ends. That's where this begins. Not with speculation about what deep space might do to a human body, but with a documented, dated, measured transition, and the very specific first thing that transition exposes you to. Voyager's instruments recorded a boundary, but instruments don't have a cardiovascular system, and they don't grow cataracts. To understand what that boundary actually means for a living body, you have to look at the only humans who have ever, even briefly, crossed a smaller version of the same line. Earth's atmosphere and its magnetic field work together as a two-part shield. The magnetosphere, generated by the churning iron core beneath our feet, deflects most charged particles before they ever reach the upper atmosphere. What gets through, the atmosphere itself absorbs. Every human being who has ever lived, until a specific handful in the 20th century, spent their entire life inside both layers at once, without ever having to think about it, the same way a fish doesn't think about water. The Apollo program broke that pattern for 9 missions between 1968 and 1972, carrying astronauts out past the Van Allen belts and beyond Earth's magnetosphere entirely, into a radiation environment no human had ever occupied before. Their trips were short. A round journey to the moon and back took roughly a week to 10 days, and even within that narrow window, something measurable happened. Astronauts reported strange flashes of light, roughly 17 an hour, appearing even with their eyes closed in a darkened spacecraft. Researchers later confirmed the cause. Individual cosmic ray particles, the same high-energy nuclei Voyager detected decades later, were striking the retina directly, triggering the optic nerve the way a photon of visible light would, except these particles weren't light. They were fragments of atoms moving at a meaningful fraction of the speed of light, passing straight through a spacecraft hull and straight through a human eye. In simple terms, the astronauts were seeing radiation, not observing its effects secondhand, but perceiving individual particles as they physically crossed the eye. That alone tells you something about what the shielding on those spacecraft could and couldn't stop. The longer-term picture is murkier, and it's worth being honest about exactly how murky, rather than smoothing it into something more dramatic than the evidence supports. A 2016 study led by Michael Delp at Florida State University compared cardiovascular mortality across 3 groups of astronauts: those who never flew, those who flew only in low Earth orbit, still inside the magnetosphere, and the small group of Apollo astronauts who went beyond it. The first 2 groups showed cardiovascular death rates of 9 and 11%, statistically indistinguishable from each other. The Apollo group showed a rate of 43%, 4 to 5 times higher. Delp's team also found that mice exposed to comparable radiation doses developed lasting damage to the blood vessel lining, a plausible mechanism for what the human data seemed to show. But the finding didn't go unchallenged, and the challenge matters as much as the original result. Later analyses, including work published by other radiation researchers within just a few years, questioned the study's methodology and, using different statistical approaches, found no significant excess cardiovascular risk at all. The honest answer, years later, is that this remains a genuinely open question in the scientific literature. What's not in dispute is the exposure itself, or the mechanism by which it could plausibly cause harm. What remains uncertain is how much it actually did. What is settled, though, is simpler and in some ways more unsettling than any single mortality statistic. For 13 days at most, a handful of astronauts stepped outside both of Earth's protective layers, and their bodies registered it immediately, at the level of individual retinal cells. before any long-term health question could even be asked. That's the effect of days, not months, not years, not the kind of multi-year transit a journey beyond the solar system would actually require. Which raises the real question underneath all of this. If a matter of days beyond the magnetosphere is enough to make the body itself report the exposure, in real time, through the optic nerve, what does the same environment do to a body across the kind of timescale interstellar distance actually demands? The particles that struck those astronauts' retinas didn't come from anywhere nearby. That's not a poetic way of putting it. It's the specific, physical reason nothing built to stop ordinary radiation can stop them. Most of what we think of as radiation, the kind medical equipment produces, the kind a dental X-ray delivers, moves as a wave or as a modestly energetic particle, and it interacts with matter in fairly predictable, containable ways. Galactic cosmic rays are not that. They are atomic nuclei, mostly protons, roughly 85% of them, with most of the remainder made up of helium nuclei, and a small fraction made of heavier elements entirely, carbon, oxygen, even iron, stripped of their electrons and accelerated to speeds that are a meaningful fraction of the speed of light. They didn't originate at the sun, or anywhere within a comfortable distance. The leading explanation, supported by decades of observation, points to supernova remnants, the expanding shockwaves left behind after a massive star exhausts its fuel and detonates. Those shockwaves act as natural particle accelerators, flinging nuclei outward and repeatedly kicking them faster as they bounce along the shock's expanding edge, in a process physicists call diffusive shock acceleration. Some of these particles have been crossing the galaxy, bouncing off magnetic fields, changing direction, losing and gaining tiny increments of energy for hundreds of thousands or even millions of years before one of them happens to cross paths with a spacecraft or a human retina. To put this in human terms, every galactic cosmic ray that reaches a spacecraft beyond the heliosphere is, in a very real sense, a message from a star that died before your ancestors existed. It has been traveling that long. It has a kind of geological patience built into its very existence, and it arrives with no warning, no direction you can predict, no schedule you can plan around, because the magnetic fields it bounced through on the way here scrambled its original trajectory into something close to random. What makes these particles genuinely dangerous, rather than merely exotic, is a specific subset within that mix, the heavy, high-energy nuclei, what radiation researchers call HZE particles, for high charge and energy. Iron nuclei moving at relativistic speed carry both significant mass and significant charge, and when a particle like that strikes matter, whether that matter is a spacecraft hull or a strand of human DNA, it doesn't deposit its energy gently across a wide area the way a lower energy particle might. It carves a dense, narrow track of ionization directly through whatever it hits, like a bullet rather than a spray of buckshot. Along that narrow track, every molecule in its path absorbs a concentrated dose of energy nearly instantaneously. Consider what that means for something as small as a single cell. A lower energy form of radiation might deposit its energy broadly enough that a cell has some chance of registering only minor, repairable damage. An HZE particle passing directly through a cell's nucleus delivers its energy along a track so narrow and so dense that the damage isn't diffuse. It's concentrated exactly where it's most consequential, in the molecule that carries the instructions for everything that cell will ever do. This is also, not incidentally, why the light flashes those Apollo astronauts described made physical sense the moment scientists understood the mechanism. A single HZE particle crossing the retina doesn't need visible light to trigger a response. Its own passage through the tissue, its own dense trail of ionization, is enough to fire the optic nerve directly. The astronauts weren't imagining anything. They were, in the most literal sense available to a human being, watching radiation move through their own eyes in real time. Here is what makes all of this relevant to a journey beyond the solar system, rather than simply an interesting historical footnote about 13 days in the 1970s. Inside the heliosphere, the sun's own magnetic field and the outward pressure of the solar wind partially deflect incoming galactic cosmic rays, reducing the flux that reaches any spacecraft still inside that bubble. Beyond the heliopause, that partial deflection ends. The particles that reach a spacecraft in true interstellar space arrive at their full, unattenuated intensity, coming from every direction across the sky, continuously, with no daylight and no nighttime, because there is no local star casting a shadow to hide behind. Voyager's instruments measured that shift precisely. The spike in cosmic ray counts the instant the heliopause was crossed. What they measured was a permanent increase in exposure, not a brief flash during a short lunar mission, but a continuous environment that a body would have to sit inside for every hour of a journey that, at any speed humanity has ever achieved, would last decades rather than days. The question that raises isn't only how much of this radiation a body would absorb, it's what a spacecraft hull, or any material humans know how to build, can actually do to stop it. And the honest answer to that question turns out to be stranger and considerably less reassuring than most people assume. The obvious answer to a dangerous particle is a thick wall. More material between you and the threat should mean more protection. That instinct, reasonable as it sounds, turns out to be one of the more consequential mistakes in the entire history of spacecraft design, and understanding why gets at something fundamental about what these particles actually are. Aluminum has been the default structural material for spacecraft since the beginning of spaceflight, for good reason. It's light, strong, well understood, and easy to manufacture into the shapes a pressurized hull requires. For most kinds of radiation, a layer of aluminum does what you'd expect. It absorbs the incoming particle, converts its energy to heat, and stops the threat there. But galactic cosmic rays, particularly the heavy nuclei within that mix, don't behave that way when they strike aluminum. Instead, the collision between an incoming iron nucleus and an aluminum atom in the hull can shatter the aluminum nucleus itself, a process called spallation. The shattering doesn't absorb the danger. It multiplies it, scattering a spray of secondary particles, additional protons, neutrons, and fragments of the original nucleus, outward in every direction, including straight through the hull toward whoever is sitting on the other side. In simple terms, hitting a heavy cosmic ray with a wall of aluminum can be like hitting a rifle round with a pane of glass. You've stopped the original bullet. You've also created a spray of shrapnel exactly where you didn't want one. Researchers studying this problem arrived at a specific, almost paradoxical finding. For certain shielding thicknesses and certain particle energies, adding more aluminum can actually increase the radiation dose a crew receives, because the added material generates more secondary particles than it blocks. The shielding in those cases isn't protecting the people inside. It's manufacturing more of the very danger it was built to stop. The material that does work, and works considerably better, is hydrogen, or anything rich in it. Water, polyethylene, the plastic used in ordinary plumbing pipe. Even, in some proposed designs, the spacecraft's own stored fuel, if it happens to be hydrogen-based. Hydrogen's advantage comes down to its nucleus. A single proton, nothing more. There's no complex internal structure to shatter, so hydrogen-rich shielding absorbs the energy of an incoming particle through direct interaction rather than fragmentation, producing far fewer secondary particles in the process. Layer for layer, hydrogen-rich material stops more of the dangerous radiation and creates less of the dangerous byproduct. For context, This is why proposals for long-duration deep space habitats increasingly favor design choices that seem almost mundane. Water tanks positioned as a shell around the crew's sleeping quarters, or supplies of drinking water and food doubling as passive shielding, simply because water is already mass the spacecraft has to carry anyway, and it happens to shield better than the metal it's flying inside of. But even hydrogen-rich shielding runs into a harder limit, one that has nothing to do with material choice and everything to do with the particles themselves. The most energetic galactic cosmic rays carry so much energy that meaningfully reducing their flux would require shielding tens of centimeters thick, sometimes calculated at a surface density equivalent to 20 centimeters of solid polyethylene or more. That much shielding, wrapped around a habitat large enough to house a crew, adds tens of tons of mass, and every additional ton of shielding is a ton that has to be accelerated, decelerated, and carried across the entire journey, at an energy cost that compounds with distance and duration in ways that make the shielding itself part of the propulsion problem, not separate from it. What this means in practice is that there is no simple engineering fix sitting on a shelf somewhere, waiting to be scaled up. The most effective known shielding material, applied in sufficient thickness to meaningfully protect a crew across a multi-year transit, would likely add more mass to a spacecraft than the crew, their supplies, and their living quarters combined. Reduce the shielding to something the spacecraft can actually carry, and it stops a fraction of the flux, while sometimes making the remainder more dangerous through the very fragmentation it was meant to prevent. This isn't a failure of imagination or funding. It's a mismatch between the physical scale of the threat and the physical scale of what a spacecraft can practically carry. And it raises the question underneath all of it, the one that actually determines what happens to a human body across a journey that shielding can only partially blunt. What does an unstoppable fraction of this radiation, absorbed continuously over years, rather than blocked in a single moment, actually do at the level of a living cell? Every cell in the human body carries the same basic repair kit, refined over roughly 4 billion years of evolution, for dealing with damage to its DNA. Ordinary radiation, the kind that comes from a dental X-ray or a background exposure to the natural radioactivity in soil and rock, breaks DNA strands in a fairly forgiving pattern. The breaks are scattered, isolated from each other, and the cell's repair machinery, systems with names like non-homologous end joining, can usually find each break, patch it, and move on, with only a small margin for error. Consider what changes when the particle doing the damage isn't a photon of low-energy radiation, but a heavy nucleus carrying enormous charge and energy, moving at a meaningful fraction of light speed. As that particle crosses a cell's nucleus, it doesn't scatter its energy the way ordinary radiation does. It deposits it in an extremely narrow, extremely dense track directly along its path. Where ordinary radiation might break a DNA strand once in an isolated spot, a single heavy particle crossing the nucleus can produce multiple breaks within a stretch of DNA, barely 1 or 2 helical turns long, close enough together that the cell's normal repair process, built to handle one clean break at a time, essentially can't pass what it's looking at. Researchers have a specific term for this: clustered damage, or complex double-strand breaks. And the distinction matters enormously, because it changes not just how much damage occurs, but whether the cell's existing tools can fix it at all. Studies comparing repair speed after exposure to ordinary radiation versus heavy particle radiation find that the clustered breaks caused by particles like iron or silicon nuclei are repaired far more slowly, and in a meaningful share of cases, not correctly repaired at all. The cell's default repair pathway, the one built for isolated simple breaks, frequently fails outright, forcing a slower, more error-prone backup system to attempt the job instead. if it manages to intervene before the cell simply dies. In simple terms, this isn't the same kind of damage the body already knows how to handle. It's a version of DNA damage that the human repair system, evolved almost entirely under the radiation conditions present on Earth's surface, is poorly equipped to fix cleanly, not because the damage is larger in total, but because it's shaped differently, concentrated in a way nothing in our evolutionary history prepared us for. What happens when a cluster of DNA breaks, goes unrepaired, or gets stitched back together incorrectly, follows one of a few paths. The cell may simply die, which, for most tissue in the body, is the least consequential outcome. New cells replace it, and the damage ends there. The more concerning outcome is a cell that survives the damage, but survives it wrong. A misrepaired strand, a chromosome rearranged in a way that alters how the cell's genetic instructions read. A mutation carried forward into every future copy of that cell. This is, mechanistically, the pathway that connects radiation exposure to elevated long-term cancer risk. A pathway researchers have documented directly by observing chromosomal abnormalities in the blood cells of astronauts after spaceflight, even relatively short spaceflight, well before any illness becomes apparent. To put this in human terms, the danger of galactic cosmic radiation isn't primarily about a single overwhelming dose arriving all at once, the way an acute radiation exposure from a nuclear accident might work. It's cumulative and quiet. Every heavy particle that crosses a cell's nucleus over the course of a years-long journey adds another small, oddly shaped scar to the body's genetic archive, most of them repaired imperfectly rather than not at all, most of them invisible for years or decades before any consequence surfaces. This is also precisely why the question of duration matters so much more than the question of a single dangerous moment. A body can often absorb a sharp, brief exposure and recover, the way the Apollo astronauts largely did across their 13-day missions. What the human body has never been asked to do, because no human being has ever attempted it, is sit inside this specific kind of damage, continuously, for years at a stretch, while every system meant to repair the harm quietly falls further behind the rate at which the harm accumulates. Which brings the question to something more concrete than biology alone can answer. If this is what happens at the level of a single cell, what number, over what time frame, actually crosses the line from tolerable to catastrophic? And how does that number hold up against the length of a real interstellar journey? Every hazard so far has been described in mechanism: how particles form, how shielding responds, how a cell absorbs the damage. What's been missing is a number, a specific threshold that tells you exactly how much of this a human body is currently permitted to absorb before an agency responsible for astronaut safety says the risk has become unacceptable. That number exists, and it comes from NASA itself. Following a 2021 review by the National Academies of Sciences, Engineering and Medicine, NASA adopted a career radiation exposure limit of 600 millisieverts, a single ceiling applied equally to every astronaut regardless of age or sex. The figure isn't arbitrary. It represents the cumulative dose at which a 35-year-old astronaut's added lifetime risk of dying from radiation-induced cancer reaches roughly 3% above the baseline risk anyone carries simply by living on Earth. Cross that threshold, and NASA's own framework says the acceptable balance between mission value and long-term harm has tipped. To put 600 millisieverts in human terms, it's roughly the dose a person would accumulate from about 200 chest CT scans, though the comparison is imperfect, since the type of radiation involved in a CT scan is far gentler, in terms of biological damage, than the heavy cosmic ray particles a deep space traveler would actually absorb. It's also, for context, more radiation than residents living near the Fukushima nuclear accident in 2011 received in the aftermath. spread across a full career of astronauts flying repeated missions, rather than years of ambient civilian exposure. Here is where the number stops being a policy detail and becomes a wall. NASA's own technical assessments, published through its research arm, state plainly that a mission to Mars, a round trip lasting roughly 2 to 3 years, would expose a crew to radiation levels that are likely to at least double that 600 millisievert career limit, even accounting for spacecraft shielding. Independent estimates in the peer-reviewed literature place the accumulated dose for a full Mars mission at 1 full sievert or more, nearly double the ceiling NASA itself considers acceptable, arrived at within a single mission rather than across an entire career. Consider what that means for a destination measured not in months of travel, but in years or decades. Mars, at its most distant from Earth's orbit relative to the Sun, sits at a maximum of roughly 2.5 astronomical units away. The nearest star beyond our own Sun sits at over 260,000 astronomical units away. If a Mars mission alone is projected to exceed NASA's lifetime safety threshold by a significant margin, a journey that would need to sustain a crew for decades rather than years, at continuous, unshielded exposure to the full, unattenuated flux of interstellar cosmic radiation, isn't simply exceeding the limit. It's operating in a dose regime the current framework was never designed to accommodate, because no space agency has ever seriously modeled a mission duration where the concept of a career limit stops being the relevant unit of measurement entirely. What this means in practice is something worth sitting with plainly. The 600 millisievert line wasn't drawn by pessimists. It was drawn by the same agency actively planning to send humans to Mars, calculated using a risk model built from decades of astronaut health data and radiobiology research. And even that agency's own internal assessments concede that its nearest, most immediate deep space goal already breaks the limit it just finished establishing. A mission to the nearest star isn't a modest step further along the same road. It's a destination where the entire concept of a lifetime radiation budget, as currently defined by the only agency with real astronaut health data to define it, simply stops applying, because no one has ever needed to ask what comes after the ceiling has already been broken by orders of magnitude. Radiation, on its own, is enough to place interstellar distances outside the boundary of what current safety science considers survivable. But radiation doesn't act on a body in isolation. It compounds with something else, something quieter, that doesn't show up in a dosimeter reading at all. The slow, measurable toll interstellar exposure takes on the mind carrying that body across the years the journey demands. Cancer risk is the number NASA tracks, because cancer risk is what shows up decades later on a chart in a mortality statistic. But there's a second consequence of this same radiation exposure that doesn't wait decades to appear, and it targets the one organ a deep space mission can least afford to lose function in, even briefly: the brain of the person responsible for keeping everyone else alive. The hippocampus, a small, curved structure buried deep in the brain, plays an outsized role in memory formation, spatial navigation, and the kind of rapid learning a crisis demands. It also happens to be unusually vulnerable to exactly the kind of dense, concentrated radiation damage heavy cosmic ray particles produce. Researchers have studied this extensively, though almost entirely in rodent models, since no ethics review board would authorize deliberately irradiating a human brain with cosmic ray equivalent particles simply to observe what happens. What those rodent studies consistently show is worth sitting with. Mice exposed to radiation doses, calibrated to match what an astronaut would absorb on a Mars-length mission, show measurable impairments in spatial memory, object recognition, and attention, appearing within weeks of exposure and, in several studies, persisting for months afterward, in some cases for as long as a year. The mechanism researchers have identified is structural, not merely behavioral. Exposed brain tissue shows a measurable reduction in the density and complexity of the branching connections between neurons, a physical thinning of the very architecture memory and learning depend on. Some studies have also found disrupted neurogenesis, a slowdown in the brain's normal process of generating new cells in the hippocampus throughout adult life, a process already understood to matter for maintaining healthy memory function. In simple terms, this isn't a claim that radiation makes an astronaut foggy or tired in some vague, hand-waving sense. It's a documented, physical change to brain structure, observed directly under a microscope, tied to specific and repeatable declines in specific cognitive tasks, in the exact regions of the brain a crew member would depend on most during an emergency, requiring fast, accurate judgment. Here is where honesty about the limits of the science matters more than anywhere else in this discussion. Every one of these findings comes from rodent studies, not human ones, and translating rodent brain physiology to human cognition carries real uncertainty. Some research groups have found that certain radiation exposures produce mixed or even counterintuitive results, depending on the specific task, the sex of the animal studied, or the particular mix of particles used. An acknowledgement that this remains genuinely active, unsettled research, rather than a fully closed case. NASA's own scientists, writing in the peer-reviewed literature, describe the chronic effects of cosmic radiation on brain structure and function as, in their own words, poorly understood, which is precisely why long-duration missions are treated as the priority research gap they represent, rather than a solved problem with a known answer. What can be said with confidence is this: the mechanism is physically plausible, structurally documented in animal models, and specifically concentrated in the exact brain regions a crew would most need to rely on. What can't yet be said with confidence is the precise magnitude of that risk in an actual human being, exposed not for months, but for the full duration of a multi-year or multi-decade interstellar transit. That gap in human data isn't reassuring. It's simply unmeasured, in the same way that no human being has ever measured what a body does after crossing the specific boundary Voyager's instruments detected in 2012. Taken together, this closes something like a full circuit on the radiation problem specifically. It begins the moment a spacecraft passes beyond the heliosphere and beyond the reach of Earth's magnetic field. It compounds cell by cell, largely undetectable, until chromosomal abnormalities and cancer risk statistics eventually surface the damage years later. And it may, separately, quietly reshape the very organ responsible for keeping a mission's decisions sound, long before any of that later damage would ever announce itself. But radiation, as thorough as this picture has become, is only one hazard among several a body would face beyond the solar system, and some of the others don't wait years, or even months, to make themselves known. Some of them begin working on the body within seconds of exposure, which is where this has to go next. Radiation works in silence, across years, invisible to the person it's damaging. Vacuum exposure works differently. If a hull breach or a suit failure ever put a human body in direct contact with the true emptiness beyond a spacecraft, the timeline would be measured in seconds, and thanks to a small number of documented accidents and a great deal of Cold War-era research, the sequence of what actually happens is known with unusual precision. Popular imagination, shaped by decades of science fiction, tends to picture something violent and immediate: a body swelling and rupturing, blood boiling, a person freezing solid within moments. Almost none of that is accurate, and the real sequence, if anything, is stranger for being so much quieter than the myth. The first and most urgent danger isn't decompression itself, it's what happens to air already inside the lungs. If a person holds their breath during sudden depressurization, the air trapped inside expands rapidly against the sudden drop in outside pressure and can tear lung tissue directly, a serious injury on its own. This is why the single most important instruction in any decompression training is the opposite of instinct. Exhale and let the air escape rather than holding it in. Assuming that's done, the next several seconds follow a documented physiological sequence. Consciousness holds for roughly 9 to 12 seconds after depressurization begins. The same window the U.S. Federal Aviation Administration formally defines as the time of useful consciousness at extreme altitude. The brief period before oxygen deprivation to the brain shuts higher function down. During that window, moisture on exposed surfaces, the tongue, the eyes, the lining of the lungs, begins to vaporize almost instantly, since water boils at far lower temperatures once the surrounding pressure drops low enough. This is ebullism, and it's real, though it's a far cry from the explosive rupture Hollywood imagines. The body doesn't burst. Water vapor and dissolved gases simply begin coming out of solution in soft tissue, causing visible but survivable swelling, not catastrophic injury, in the brief window before unconsciousness. We know this timeline isn't theoretical because it's been observed directly more than once. In 1966, a NASA test technician named Jim LeBlanc was performing a routine spacesuit test in a vacuum chamber when his suit's air hose disconnected. He later reported that the last sensation he remembered before losing consciousness in roughly 12 to 15 seconds was the saliva on his tongue beginning to boil. Chamber operators noticed the failure and began repressurizing within seconds. LeBlanc regained consciousness as pressure was restored and, by his own account, felt well enough to go back to work later that same day with no lasting injury. A far more serious case unfolded aboard the Soviet Soyuz 11 spacecraft in 1971. A valve accidentally opened during the crew's return to Earth, venting the cabin's atmosphere into the vacuum of space over roughly 30 seconds. One crew member managed to partially close the valve before losing consciousness. All 3 cosmonauts died, the only human deaths to occur in the vacuum of space itself. And the accident remains, to date, the reason spacecraft cabin design and crew procedures treat depressurization as one of the most rigorously guarded against failure modes in all of spaceflight. To put these 2 cases side by side, roughly 30 seconds without pressure, and the outcome moved from a full, uneventful recovery to a fatality for an entire crew. Research using animal subjects in the decades since has refined the window further, generally placing the boundary between survivable and fatal exposure somewhere around 90 seconds, assuming prompt repressurization, with exposures beyond about 2 minutes considered almost universally unsurvivable. What this means in practice, for a journey beyond the solar system, isn't that vacuum exposure is the primary threat across a multi-year transit. Spacecraft hulls, properly maintained, are not expected to fail catastrophically under normal operation. But it does mean that unlike radiation, which accumulates slowly and grants years of margin for a mission to notice and respond to a problem, a single hull breach, a single failed seal, a single micrometeorite strike in exactly the wrong place converts survival into a countdown measured in seconds rather than years. Across a mission lasting decades, with no possibility of resupply, rescue, or repair support from Earth, that kind of failure mode doesn't need to happen often to be catastrophic. It needs to happen once. Vacuum, though, isn't the only environmental hazard waiting on the other side of a compromised hull. There's a second one, and it works by an almost opposite mechanism, one that surprises most people who assume the danger of deep space is simply cold. Almost everyone assumes the primary temperature danger of deep space is cold. It's an understandable assumption, and it's also, for a crewed spacecraft with an intact hull, close to backward. Heat moves from one place to another through exactly 3 mechanisms: conduction, the direct transfer between touching materials; convection, the transfer carried by a moving fluid, like air circulating in a room, and radiation, the emission of heat directly as infrared energy without needing any material medium at all. On Earth, in a room, in a spacecraft cabin with air inside it, all three mechanisms work together, and convection in particular does most of the quiet, unnoticed work of keeping a warm object from simply cooking in its own generated heat. Air moves across your skin, carries heat away, and gets replaced by cooler air. It's such a constant, background process that almost no one thinks about it. In the vacuum outside a spacecraft's hull, convection simply doesn't exist. There's no air to carry heat away, no fluid medium of any kind. Heat can only leave a spacecraft, or a suited astronaut, through conduction to something directly touching them, or through radiation, infrared energy, leaving the body or the hull and traveling outward into the emptiness of space. And radiation, as a cooling mechanism, is dramatically less efficient than convection at the temperatures and heat loads a human body or an operating spacecraft actually produces. Consider what that means in practice. A spacecraft generates heat constantly, from the electronics running its systems, from onboard machinery, and from the crew themselves. A resting adult human body produces roughly the same heat output as a small space heater, continuously, simply by being alive. On Earth, that heat disperses easily into the surrounding air. Inside a sealed spacecraft in vacuum, with no convection available, that same heat has nowhere obvious to go. It has to be actively collected and radiated away by design, using dedicated systems, or it simply accumulates. This is why astronauts working outside the International Space Station in a pressurized suit face a genuinely counterintuitive engineering problem. Direct sunlight on one side of the suit can push surface temperatures above 120 degrees Celsius, while the shadowed side, with no sunlight and no atmosphere to hold or transfer warmth, can drop toward negative 160 degrees Celsius, an extreme swing occurring simultaneously across a single suit. But the more persistent, day-to-day danger inside that suit isn't the shadowed cold. It's the astronaut's own metabolic heat, generated continuously by the physical effort of the spacewalk itself, with nowhere to escape to except through an active cooling system built directly into the suit. That system, called a liquid cooling and ventilation garment, works by circulating chilled water through a network of tubes worn against the skin, pulling heat away from the body and carrying it to a radiator that vents the excess as infrared energy into space. Without that system actively running, an astronaut generating heat through physical exertion inside a sealed, insulated suit would, counterintuitively, be at meaningfully greater risk of overheating than freezing, because there's no passive mechanism, no breeze, no convective airflow capable of carrying that excess heat away on its own. To put this in human terms, space isn't cold in the way a winter night is cold, where the danger is heat leaving your body faster than you can replace it. Space is thermally inert in a stranger way. It has almost no capacity to either warm you or cool you passively, and every degree of temperature control a human body needs, in either direction, has to be actively engineered and actively maintained for the entire duration of the exposure, without a single moment of the passive assistance a planet's atmosphere provides for free. For a mission lasting decades, that reframes the thermal problem entirely. It isn't a question of surviving the cold of deep space. It's a question of whether an active thermal management system, dependent on pumps, radiators, and coolant loops, can run without failure, without a single serious malfunction, for the entire length of the journey. Because the moment it stops, there is no atmosphere standing by to gently absorb the difference. Radiation compounds silently over years. Vacuum exposure kills in seconds if it ever occurs. Thermal failure sits somewhere in between, a slower unraveling that depends entirely on mechanical systems holding together far longer than any comparable system has ever been asked to. And that dependence on mechanical systems functioning flawlessly, without failure, across years rather than days, is itself the next hazard worth examining directly. Every hazard covered so far assumes a spacecraft actually arrives at its destination on some kind of survivable timeline in the first place. That assumption deserves scrutiny on its own, because the engines humanity currently knows how to build were never designed for interstellar distance. They were designed for something else entirely, and the mismatch between the two isn't a matter of degree. It's a difference in kind. Rocket engines are typically compared using a measurement called specific impulse, essentially a measure of how efficiently an engine uses its fuel, expressed as the exhaust velocity divided by gravitational acceleration. Chemical rockets, the kind that have launched every human being who's ever left Earth, burn a fuel and an oxidizer together to release energy fast and violently, producing enormous thrust but relatively low specific impulse. That combination is exactly right for one job: fighting Earth's gravity during the first minutes of a launch, when raw thrust matters more than fuel economy. It's exactly wrong for a different job: sustaining acceleration continuously across the months or years a longer journey would demand, because the fuel efficiency simply isn't there. A chemical rocket, carrying enough propellant to accelerate meaningfully toward a fraction of light speed, would need to carry more fuel mass than any vehicle could physically launch. Ion propulsion solves the efficiency half of that problem and creates a different one in its place. Rather than burning fuel, an ion thruster uses electric fields to accelerate a stream of charged particles, typically xenon, out through a nozzle at speeds far exceeding what chemical combustion can achieve, extracting dramatically more velocity from every gram of propellant. NASA has already flown this technology successfully, most notably aboard the Dawn spacecraft and the earlier Deep Space One probe, using engines with specific impulse many times higher than any chemical rocket. But that efficiency comes at a steep cost, one that becomes obvious the moment you look at the actual thrust these engines produce. NASA's advanced ion engine prototypes generate maximum thrust measured in a few hundred millinewtons, a force so small it's roughly comparable to the weight of a single sheet of paper resting in your palm. In simple terms, an ion engine sips fuel with extraordinary efficiency, but it pushes so gently that building meaningful speed requires firing continuously, uninterrupted, for months or years, gradually and patiently accumulating velocity the way a marble might, if nudged forward by the same small breath of wind, over and over, for a very long time. That trade-off, high efficiency paired with vanishingly low thrust, works well for the missions ion propulsion has actually flown. Unmanned probes with no crew to keep alive, no urgent timeline, and years to spare for a gradual build-up toward a modest final velocity. It becomes a fundamentally different problem when the destination isn't a nearby asteroid or a planet a few years away, but a star system requiring a cruise velocity of 10% of light speed just to keep a mission's total duration within a human lifetime. Reaching that speed using anything resembling current ion propulsion technology would require centuries of continuous, uninterrupted thrust, an operational demand no engine and no engineered system of any kind has ever come close to sustaining. What this means in practice is that the two propulsion families humanity has actually built and flown sit at opposite ends of a spectrum, and neither end reaches the destination this discussion started with. Chemical propulsion has the thrust, but not remotely the efficiency. Ion propulsion has the efficiency, but not remotely the thrust. Fusion-based propulsion, still purely theoretical at any scale that could power a real spacecraft, is the design researchers describe as the only concept that could plausibly deliver both high thrust and high efficiency at once. And it remains, by every honest engineering assessment, a solution that doesn't yet exist outside of research papers and physics, that has never been demonstrated at anything close to the necessary scale. None of the other hazards in this discussion, not the radiation, not the vacuum, not the thermal balance, matter if the ship never generates enough velocity to complete the journey within any time frame a crew or a civilization's patience could sustain. And that raises a question distinct from propulsion itself. Even setting the engine problem aside entirely, could the closed systems responsible for keeping a crew alive, breathing, fed and hydrated, actually run without failure for as long as any of these propulsion concepts would require? Every previous hazard has, in some sense, been about what the environment beyond the solar system does to a human body from the outside. This one is different. It's about whether the machinery meant to keep that body alive can actually run without interruption for as long as the journey demands, entirely on its own, with no possibility of a supply ship arriving to fix what breaks. The technical name for that machinery is the Environmental Control and Life Support System, and the only place humanity has ever operated a real version of one, continuously, with people living inside it, is the International Space Station. Since 2007 and 2008, respectively, the station's oxygen generation system and water recovery system have been running what engineers call a closed loop, reclaiming moisture from the crew's breath, sweat, and even their urine, purifying it back into drinking water, and splitting a portion of that water through electrolysis to generate breathable oxygen. It's a genuinely impressive piece of engineering, and it's also, even now, not a fully closed loop at all. Consider the actual numbers. The ISS system recovers roughly 90% of the water that passes through it, not all of it. 90%, meaning a meaningful fraction is lost to the process every single cycle, water that has to be replaced from somewhere, because a system that only returns 9/10 of what it processes runs a permanent compounding deficit if nothing external ever tops it back up. Nitrogen for the station's atmosphere isn't recycled at all. It's simply carried up from Earth and replenished by resupply missions as needed. And oxygen generation, water purification, and carbon dioxide removal collectively depend on components that fail, wear out, and require ongoing maintenance, drawing directly on crew time and a steady supply of spare parts, filters, and replacement hardware delivered from the ground on a regular schedule. In simple terms, even the most sophisticated closed-loop life support system humanity has ever built and operated isn't actually closed. It's closed enough to dramatically reduce, but not eliminate, the need for resupply, and it has never once been asked to run for years on end without a cargo vehicle eventually arriving to replace a failing pump, restock a chemical filter, or simply top off what the 90% recovery rate quietly lost along the way. NASA's own engineers, tasked with assessing whether ISS-derived technology could support a 3-year Mars mission, have studied this question directly, tracking the actual maintenance history, failure rates, and hardware lifespans of the station's water and oxygen systems, specifically to answer it. Their surveys treat equipment reliability and crew maintenance time as a direct proxy for whether current technology is ready for a mission with no resupply option at all. The honest, published assessment isn't a confident yes. It's an ongoing engineering question, actively being worked, precisely because the gap between what's been demonstrated on a resupplied station in low Earth orbit and what a genuinely self-sufficient, multi-year, unsupported mission would require remains real and unresolved. To put this in human terms, imagine a well-designed, to never run dry, built by the best engineers alive, that nonetheless quietly loses a small amount of water every single day it operates. On a station orbiting a few hundred kilometers overhead, with a cargo ship scheduled to visit every few months, that loss is a manageable inconvenience. On a vessel 4 light-years from the nearest resupply option, with no cargo ship ever coming, that same small daily loss becomes a slow-motion, unstoppable countdown, the exact rate of which would need to be solved with total, engineered certainty before departure, because there would be no opportunity to solve it correctly the second time. This is why serious mission designers increasingly look past ISS-style physical and chemical recycling entirely, toward what are called bioregenerative systems, closed ecological loops that use living plants, algae, or engineered microbial communities to recycle waste and regenerate oxygen and food together, mimicking, in miniature, the way Earth's own biosphere sustains itself. The European Space Agency has spent decades developing one such concept, a multi-compartment system modeled loosely on a lake ecosystem. It remains, after all that research, a laboratory-scale demonstration, not a flight-proven technology capable of sustaining a human crew for the length of time this journey would actually require. Which leaves the honest state of the science exactly where the ISS data leaves it. Humanity has built and operated a closed-loop life support system that works, reliably, for years at a time, provided a supply chain from Earth remains intact. What has never been built, tested, or even attempted is a version of that same system with the supply chain permanently and completely removed. And even if every mechanical, chemical, and biological system aboard a ship somehow ran flawlessly for the entire journey, there's a separate question that no amount of engineering redundancy alone can answer. What does a body confined to that same closed environment without gravity actually do to itself across years rather than months? Gravity is so constant a presence in a human life that it barely registers as a force at all. It's simply the backdrop against which every bone, every muscle, and every heartbeat has developed for the entire span of human evolution. Remove it, and the body doesn't adapt gracefully. It begins, almost immediately, dismantling structures it no longer believes it needs. Bone is not the inert scaffolding it's often imagined to be. It's a living tissue, constantly being broken down and rebuilt in response to the mechanical stress placed on it, a process that depends heavily on the simple, repeated load of standing, walking, and moving against Earth's gravitational pull. In microgravity, that loading disappears almost entirely, and the body responds by resorbing bone tissue faster than it replaces it. Multiple independent studies, including a systematic review of data from over 100 astronauts, converge on a consistent figure. Bone loss during spaceflight proceeds at roughly 1 to 2% per month, concentrated most heavily in the weight-bearing bones of the lower body and spine, the exact regions that carried the most load back on Earth. To put that rate in human terms, over a typical 6-month mission aboard the International Space Station, astronauts can lose as much as 10 to 20% of bone mineral density in the hip and pelvis, a level of loss researchers have directly compared to the osteoporosis seen in elderly women on Earth, except compressed into a matter of months, rather than accumulated across decades. And unlike most spaceflight adaptations, this one doesn't simply reverse once the body returns to gravity. Studies following astronauts for a full year after landing have found that bone density in some regions of the spine remains measurably below its pre-flight baseline, even 12 months later, evidence that at least some of this loss may be effectively permanent rather than merely temporary. Muscle tells a similar story through a different mechanism. Deprived of the resistance that ordinary movement against gravity normally provides, skeletal muscle simply stops receiving the biological signal to maintain its own mass, and protein synthesis within muscle tissue can drop by nearly half. Studies of 6-month ISS missions have documented muscle loss reaching 12 to 20% in specific muscle groups, including a 20% reduction in some of the postural muscles along the back. translating into a 25 to 30% loss in the force those muscles can generate. Left completely unaddressed, researchers estimate muscle loss on a long-duration mission could climb as high as 50%. What keeps those numbers from being far worse is not the body's own resilience. It's a deliberate, unrelenting countermeasure. Astronauts aboard the ISS exercise on specialized equipment for roughly 2.5 hours a day, 6 days a week, specifically engineered to simulate the loading gravity would otherwise provide. Even with that daily commitment, astronauts still return from typical 6-month missions, having lost an average of several percent of bone density at the spine and hip. The exercise regimen doesn't prevent the loss, it slows it to something survivable. In simple terms, keeping a human body intact in microgravity isn't a passive matter of waiting it out. It requires active, daily, disciplined physical effort, sustained without interruption, for the entire length of the mission, and even then, the body still loses ground it may never fully recover. For a 6-month mission, that's a manageable, well-studied cost. Extend the same monthly rate of loss across the years or decades an interstellar crossing would require, and the arithmetic becomes considerably harder to look away from, even accounting for the fact that some bone loss appears to plateau over time rather than continuing linearly forever. No astronaut, in the entire history of spaceflight, has ever spent more than about a year in microgravity at a single stretch, which means the honest answer to what happens at the 5-year mark, the 10-year mark or beyond, is that no one actually knows, because no human body has ever been asked to find out. Consider, too, that bone and muscle are only the most visible casualties. Microgravity also causes fluid within the body to redistribute upward, toward the head and chest, altering cardiovascular function in ways researchers are still working to fully characterize, along with documented changes to eyesight from pressure shifts around the optic nerve. Each of these compounds with the others, and all of them compound with the radiation damage, the confined quarters, and the total absence of the countless incidental forms of physical stimulation Earth provides simply by existing. None of this, notably, has anything to do with the mind. The body can be measured, tracked, and at least partially defended against with equipment and discipline. What happens to human psychology, confined for years inside the same small volume of space, with the same small group of people, and no possibility of leaving, turns out to be a harder problem to engineer a countermeasure for. Every hazard covered to this point can, in principle, be measured with an instrument, a dosimeter, a bone density scan, a pressure gauge. The next one is harder to measure, and in some ways, harder to defend against, because the thing being damaged is the very capacity a crew would need to notice that anything was going wrong. No human being has ever attempted a true interstellar journey, so no direct psychological data exists for one. What does exist is a body of research on the closest approximations science has been able to construct, missions and environments that share the isolation, the confinement, and the delayed or absent contact with the outside world, without the actual distance or danger of deep space itself. The most extensive of these was Mars 500, a joint Russian and European project that sealed 6 crew members inside a windowless facility for 520 days, the approximate round-trip duration of a real Mars mission, with no way out and no possibility of rescue if anyone changed their mind. Researchers tracking the crew's mood, hormone levels, and behavior over that time documented a consistent, well-established pattern also seen in Antarctic winter-over cruise and submarine deployments, sometimes called the third quarter phenomenon, an initial period of heightened alertness and enthusiasm, followed by a difficult stretch after the mission's halfway point, when the novelty has worn off, but the end still feels distant, before a final period of renewed focus as the finish comes into view. Within Mars 500 specifically, researchers observed measurable increases in interpersonal tension, and documented fluctuations in group cohesion, concentrated especially in that middle stretch of the mission. A separate, more recent line of research has gone further and found something genuinely striking. Isolation doesn't just affect mood. It appears to physically reshape the brain. A study of 25 crew members who spent 12 months at Antarctica's Concordia station, one of the most isolated research outposts on Earth, used MRI scans taken before, immediately after, and 5 months following the deployment. The crew showed measurable decreases in gray matter across several brain regions, including the hippocampus, the same structure independently implicated in the cosmic radiation research covered earlier in this discussion, along with a broader reduction in overall white matter. Encouragingly, most of these changes reversed within 5 months of returning to a normal environment. But the fact that isolation alone, without any radiation exposure at all, produces a measurable structural change in the brain is a finding worth sitting with on its own. In simple terms, prolonged isolation isn't simply an emotional or motivational challenge to be managed with good morale and team-building exercises. It appears to leave a physical signature in brain tissue, a signature that, in the Antarctic study at least, needed months back in a normal environment to recover, an option that, for a multi-year transit far beyond the solar system, simply wouldn't exist. What makes this hazard particularly difficult to plan around, compared to almost everything discussed so far, is the honest limitation researchers themselves consistently flag. Every one of these studies, Mars 500, HICs, Antarctic winter overcruise, caps out at somewhere between 8 months and a little over a year and a half. None of them approach the multi-year, and for a true interstellar journey, multi-decade duration this discussion is actually built around. Researchers studying high seas have written plainly that even their longest missions don't fully capture what a multi-year Mars expedition would demand psychologically, let alone something considerably longer still. And unlike an Antarctic research station or a sealed Earth-based facility, a real interstellar mission offers no analog researchers have ever been able to construct for the specific psychological weight of genuine, irreversible distance, the knowledge that Earth isn't simply far away, but essentially unreachable for the rest of a crew member's natural life. None of the isolation research suggests catastrophic, mission-ending psychological collapse is guaranteed. Mars 500's crew, for what it's worth, also reported genuine increases in positive emotion and camaraderie at points across their mission, evidence that human beings can and do adapt meaningfully to extreme confinement. What the research does suggest, consistently and across every analog environment scientists have been able to build, is that isolation of this kind exacts a real, measurable cost on mood, on cohesion, and now, it appears, on brain structure itself, and that cost has never once been tested at anything close to the timescale an interstellar mission would actually require. There is one more variable in this entire discussion that has nothing to do with biology, engineering, or psychology at all, and it may be the strangest one of all, because it doesn't threaten the crew's survival so much as it quietly rewrites the very meaning of the word home they'd be trying to return to. Every hazard so far has assumed a shared, simple starting point, that a body traveling toward another star and a body remaining on Earth are both experiencing time the same way, simply from different vantage points. Special relativity says that assumption is wrong, and it says so with a level of experimental confirmation that leaves very little room for doubt. Einstein's 1905 theory of special relativity established that time itself isn't a fixed, universal backdrop shared identically by everyone. It flows at a rate that depends on how fast an observer is moving relative to someone else. Specifically, the faster an object travels relative to a stationary observer, the more slowly time passes for that moving object, from the stationary observer's point of view. This isn't a mechanical quirk affecting clocks specifically. It's a property of space-time itself, and it's been confirmed repeatedly through direct experiment. Atomic clocks flown aboard aircraft measurably drift out of sync, with identical clocks left on the ground, and GPS satellites, orbiting at roughly 14,000 kilometers an hour, require constant relativistic correction, because without it, positioning errors would accumulate at a rate of about 11 kilometers a day. The effect is governed by a single value physicists call the Lorentz factor, which depends only on velocity as a fraction of the speed of light. At the everyday speeds human beings actually experience, the Lorentz factor is so close to exactly 1 that the effect is utterly imperceptible. It only becomes meaningful as velocity climbs toward a significant fraction of light speed itself. Consider what this means at the propulsion speeds discussed earlier in this exploration. A cruise velocity of 10% of light speed, roughly the outer edge of what a mature fusion drive might theoretically achieve, produces a Lorentz factor of only about 1.005. In simple terms, for every 1,000 days that pass for a crew traveling at that speed, roughly 5 additional days would pass back on Earth. It's a real, physically measurable effect, but a modest one, nowhere near enough to meaningfully shorten the subjective length of a decades-long crossing. The effect becomes dramatically more pronounced only at speeds far beyond anything current propulsion concepts can plausibly deliver. Consider a spacecraft capable of reaching 80% of light speed, a velocity no known propulsion system, fusion-based or otherwise, has ever been seriously projected to achieve for a crewed vessel. At that speed, a journey to a star 4¼ light-years away would take a little over 5 years, as measured by mission control back on Earth. But for the crew aboard the ship, time dilation would compress their own experience journey to roughly 3½ years, nearly 2 years shorter, purely as a consequence of their velocity relative to Earth. To put this in human terms, the crew and everyone they left behind would, quite literally, stop agreeing on how much time had passed, not as a matter of perception or delayed communication, but as a fundamental, physical fact about the 2 different paths each of them took through space-time. A twin who stayed on Earth and a twin who made such a voyage would, upon reunion, have aged by different amounts, a scenario physicists have studied for over a century under the name of the twin paradox, resolved unambiguously in relativity's favor by direct experimental confirmation, not merely theoretical argument. What makes this genuinely relevant to interstellar travel, rather than simply a curiosity, is what it implies about propulsion requirements. Meaningful time dilation, the kind that could compress a multi-decade subjective journey into something a human crew's remaining lifespan could comfortably absorb, requires velocities so extreme that every other hazard in this discussion, the radiation, the fuel mass, the shielding, scales upward in direct proportion. The propulsion technology capable of delivering speeds where relativity meaningfully helps is, by a wide margin, more advanced than anything currently understood well enough to design, let alone build. So even this, one of the few genuinely strange gifts physics offers to a hypothetical interstellar traveler, arrives with a catch. It only becomes useful at exactly the velocities that make every other problem in this discussion harder to solve, not easier. Time dilation doesn't rescue an interstellar mission from its other burdens. It simply changes the shape of the bill, and only once the ship has already found a way to move fast enough that the bill was already going to be enormous. Which brings this exploration to something worth doing honestly, now that every individual hazard has been laid out on its own, not which one hazard would kill a human body first, in isolation, but what actually happens when all of them are layered together, exactly as they would be aboard a single real ship. Laid out one at a time, each of these hazards has its own clean shape, its own mechanism, its own timeline. Radiation compounds quietly across years. Vacuum kills in seconds if it occurs at all. Bone and muscle erode on a schedule measured in months. Isolation reshapes the mind slowly enough that the person experiencing it might not notice until well after the damage has set in. Laid end to end like that, in the order this discussion has moved through them, it can start to sound almost procedural, a checklist rather than a lived experience. That orderliness is, in an important sense, an illusion created by the format of explaining one thing at a time. Aboard an actual ship, none of these hazards would wait politely for their turn. They would all be happening simultaneously, from the moment the vessel crossed the heliopause to the moment, if it ever came, that it reached its destination. And when systems compound rather than proceed one after another, the honest answer to the question this exploration is built around, what would actually kill a person first, becomes considerably less clean than a ranked list. Consider how these hazards actually interact rather than simply coexist. Radiation damage doesn't only raise long-term cancer risk in isolation. Research has found that combined stressors, radiation exposure layered on top of the physiological strain of microgravity, appear in some studies to compound each other's effects, rather than simply adding together, a phenomenon researchers are still working to fully characterize. A body already weakened by months of muscle and bone loss may have less physiological reserve to withstand the cumulative cellular damage radiation inflicts. A mind already strained by isolation and confinement may be less equipped to catch and correct the kind of engineering or medical problem that, caught early, might have been manageable and left unaddressed, becomes catastrophic. None of these systems fail in a vacuum, so to speak. They fail into each other. This is also where honesty about the limits of current science matters most, more than anywhere else in this entire discussion. Every individual hazard covered so far rests on real, published, peer-reviewed research. NASA's radiation limits, the ISS's actual maintenance history, the Mars 500 and Antarctic isolation data, the rodent studies on cognitive decline. But the specific question of which failure would actually incapacitate a real human crew first, on a real multi-decade voyage, layering all of these compounding stresses together at once, is not a question any of that research has directly answered, because no mission remotely like this has ever been attempted. Extrapolating from 6-month ISS missions and 520-day isolation studies to a journey lasting decades involves real uncertainty, and the honest scientific position is to say so plainly rather than manufacture false confidence in a specific answer. What can be said with confidence, because it's a direct consequence of the actual data covered throughout this discussion, is something closer to a range of likely failure modes rather than a single verdict. Radiation-induced cancer risk becomes statistically significant on a timescale of years, well within any interstellar mission's duration, but its lethal consequences typically wouldn't manifest until well after exposure, sometimes decades later. Cognitive and psychological decline, by contrast, based on the isolation and radiation research together, could plausibly begin degrading a crew's decision-making capacity within the first few years, long before any single dramatic failure occurred, quietly raising the odds that a smaller, survivable problem, a mechanical fault, a medical emergency, a navigational error, gets caught too late or handled incorrectly. Mechanical and life support failure, given that no closed-loop system has ever run for more than a small fraction of the necessary duration without resupply, represents perhaps the single most probable point of catastrophic sudden mission failure, precisely because it's the one hazard on this entire list that current engineering has never been asked to sustain for anywhere near the required timescale. If there's a genuine answer to what would kill a person first beyond the solar system, it may not be any single hazard at all. It may be the compounding, a body already weakened by radiation and bone loss, a mind already strained by years of confinement, faced with a mechanical failure that a healthier, more rested, less isolated crew might have caught and solved in time. Not a single villain. A slow accumulation of smaller vulnerabilities, each one manageable in isolation, each one studied, documented, and real, arriving together in a way no analog mission has ever fully replicated, because no analog mission has ever needed to run long enough to find out. Every hazard in this discussion, radiation, vacuum, thermal balance, propulsion, life support, microgravity, isolation, and the strange arithmetic of relativity, was studied and documented by real people, working on real, named projects, most of them still active today. It's worth pausing on that fact directly, because it's easy for a list of obstacles this long to start sounding like an argument that no one is even trying. The opposite is true. Take the most ambitious unmanned proposal seriously pursued in the modern era. In April of 2016, the physicist Stephen Hawking stood alongside the venture investor Yuri Milner in New York to announce Breakthrough Starshot, a $100 million research program with a genuinely audacious goal, using an enormous ground-based laser array to accelerate a fleet of gram-scale probes, each attached to a reflective sail, to roughly 20% of the speed of light, aiming them at the Alpha Centauri system. The project's technical foundation came from research by physicist Philip Lubin at the University of California, Santa Barbara, and statistician Gary Hughes at Cal Poly. Work serious enough that NASA itself had already funded an early feasibility study through its innovative Advanced Concepts program before Milner's involvement began. The project's advisory board included Mark Zuckerberg, former NASA Ames director Pete Worden, physicist Freeman Dyson, whose own nuclear pulse propulsion concepts from the 1950s were referenced earlier in this discussion, and former astronaut Mae Jemison. What makes Starshot worth discussing honestly isn't its scale of ambition, it's what actually happened next, because the project's real trajectory says something true and important about the distance between a compelling idea and a completed mission. Nearly a decade after that announcement, the project has spent a small fraction of its promised funding, roughly $4.5 million of the $100 million originally pledged, and has yet to resolve fundamental engineering questions. How to build a laser array powerful enough to do the job without becoming, in effect, an unavoidable weapon of unprecedented power. How to keep a beam that powerful, precisely focused on a sail smaller than a postage stamp, across millions of kilometers of atmospheric distortion. How a probe, traveling at a meaningful fraction of light speed, could survive collision with even a single dust grain along the way. None of this reflects failure of imagination or a lack of serious scientific commitment. It reflects something closer to the honest shape of the problem itself. Even a mission with no crew to keep alive, no life support to maintain, no radiation shielding heavy enough to protect a human body, using probes so small they weigh only grams, has run into exactly the kind of engineering wall this entire discussion has traced from a dozen different angles. The distance between what's theoretically permitted by physics and what current institutions, funding structures, and engineering capability can actually deliver on any predictable timeline. Every space agency actively engaged in this question, NASA, the European Space Agency, and the independent research groups studying propulsion, radiation shielding, and closed-loop life support, are, in effect, working the same list of problems from different angles, using the same underlying physics, running into the same underlying limits. That convergence isn't evidence of a lack of imagination. It's evidence that the limits are real, shared, and not particular to any one team's specific approach. There's a useful way of thinking about problems like this, borrowed from the philosophy of technology. The difference between something being theoretically possible and something being practically accessible. It's theoretically possible to walk from New York to Beijing. The human body is entirely capable of the physical act of walking that distance. But an ocean sits in the way, And that ocean transforms a theoretical possibility into something that, for any individual actually standing on the shore, functions as an effective impossibility, not because physics forbids the crossing, but because no one has yet built the means to complete it. The nearest star is humanity's ocean in exactly that sense. The path exists. Nothing in physics rules it out. What's missing isn't permission. It's the capability, and every serious, well-funded, carefully engineered project that has ever tried to close that gap, Orion, Daedalus, Starshot, has run headlong into the same wall at a scale current civilization has not yet learned how to overcome. This isn't where the story has to end in despair, though. There's a way of holding all of this that isn't about failure at all, and it deserves to be said plainly. In the quiet stretch of thought this exploration is heading toward now. There's a difference between knowing exactly how something could kill you and that thing having already won. It's a distinction easy to lose sight of after moving through radiation damage and vacuum exposure and bone loss and isolation research, one careful mechanism at a time. And it's worth recovering here, deliberately, before this exploration comes to rest. Every hazard traced through this discussion is real. None of it was softened or invented for effect. The 600 millisievert limit is a real number, adopted by a real space agency, grounded in real cancer risk modeling. The bone loss rates, the muscle atrophy, the closed-loop water recovery figures, all of it comes from instruments, from peer-reviewed measurement, from actual human beings who volunteered their bodies and their years to generate the data this discussion has leaned on throughout. None of it is exaggerated for the sake of a more dramatic conclusion. If anything, an honest accounting understates the difficulty, because the compounding effects between these hazards, the way isolation might slow a crew's reaction to mechanical failure, the way radiation-weakened tissue might respond differently to the physical strain of a multi-year confinement, remain genuinely understudied, simply because no mission has ever run long enough for anyone to measure them directly. And yet, knowing precisely where the danger sits, in exhaustive, unflinching, well-sourced detail, is not the same thing as the danger having already prevailed. It's closer to the opposite. Every one of the obstacles catalogued here was identified, measured, and understood by people who were trying to solve it, not people who had given up on the possibility. The 600 astronauts who have flown to space, the engineers who mapped bone density loss to the 0.1%, the researchers who spent 520 days sealed in a facility to understand what isolation actually does to a human mind, the physicists who calculated exactly how much fuel a fusion drive would need and exactly why it isn't enough yet. All of them were engaged in the long, patient, unglamorous work of turning an impossible problem into a merely enormous one. That's not a small distinction. It's the entire difference between a closed door and a door that hasn't been built yet. Human beings have crossed genuine oceans before, using nothing more sophisticated than wood, canvas, and an incomplete understanding of the currents that could kill them. They did not know, when they set out, exactly how the crossing would go. They knew only that the crossing was, in principle, survivable, if enough of the right problems could be solved in the right order, by people willing to spend a very long time solving them. The distance to another star dwarfs any ocean ever crossed by a margin that borders on incomprehensible, and every hazard laid out across this discussion is real, sobering, and entirely unresolved by current technology. But every one of them is also, at least in principle, a solvable engineering and biological problem rather than a law of physics that forbids the attempt outright. Nothing here says the crossing cannot happen. Everything here says it hasn't happened yet, and that the gap between those two statements is measured, honestly, in centuries rather than years. What would kill you first, out there, beyond the reach of the only star that has ever protected you, is not really the question this exploration was built to answer with a single, definitive name. It was built to show you the actual shape of the wall, drawn as precisely as the evidence allows, so that the wall stops being an abstraction and starts being something concrete enough to actually study, to actually work on, to actually someday begin taking apart, one carefully solved problem at a time. For now, though, there's a simpler way to hold everything this exploration has covered, not as a catalogue of ways to die, as a map of exactly how far the light of a single, ordinary star reaches, and exactly how much has to be built, invented, and understood before a human body could ever safely stand outside its reach for good. You have been listening to this for a while now, here in the dark, in the quiet, wherever you happen to be lying still tonight. And somewhere above you, whether you can see it through a window or simply know it's there, the same sky holds the star this entire exploration was built around, closer to you, in the strange arithmetic of the cosmos, than almost anything else out past the edge of what you call home. What would kill you first, beyond the solar system, was never really a single answer waiting to be found, the way a name waits at the bottom of a quiz. It was always a shape, made of radiation and silence, and slowly failing machinery, and a mind straining to hold itself together across years, with no shore in sight. That shape is real. It has been measured, in sieverts and percentages and months of muscle loss, by people who gave their bodies to the measuring. And that same shape is also, somehow, still just the edge of a map, not a wall with no door in it. Every hazard traced tonight was a problem someone was actively working to solve, not a verdict already handed down. Consider, for a moment, what actually stands between you and the emptiness beyond the heliosphere. Not distance exactly, not really. A magnetic field generated by a molten iron heart you will never see, curving gently around an entire planet, like a hand cupped around a candle flame in the wind. That's what has been keeping every hazard in this exploration at bay for the whole of your life, without you ever once having to think about it. Every person who has ever lived, save a handful of astronauts on a handful of missions lasting a handful of days, has spent their entire existence inside that cupped hand, warm, protected, entirely unaware that protection was ever a question at all. Somewhere past that curved edge of magnetic field, past the reach of the solar wind, in the region Voyager crossed in the summer of 2012 and quietly kept transmitting from ever since, the particles that would begin, slowly, patiently, to take a human body apart are already streaming past, in every direction, all the time, indifferent to whether anyone is there to receive them. They have been doing that for longer than there have been humans to measure them. They will keep doing it long after this particular conversation and the person listening to it are gone. But not here, not yet. Here, tonight, the hand is still cupped, the candle is still lit, and whatever waits on the other side of that curved, quiet boundary can wait a little longer too, while you close your eyes and let the whole enormous, unfinished question drift, gently, out of reach.